Hi, so I'm going to talk about Agile Biosensor development powered by the Julie database, which is a proprietary cloud database from Zimmer Peacock. So the starting point in Agile Biosensor development is actually to have a formulation. So you have a formulation that you've kind of developed in the lab, you've got from the literature, you've got IP on it, but you've got some sort of basic formulation that works. Now, in order to kind of make that formulation deliver you signal, you need to put a sample onto that sensor, and then you need to have an excitation protocol. So here I've shown the idea that we're using cyclovoltammetry, but you can just as well be talking about amperometry or things like impedance spectroscopy. Now, that voltammetry will give you a voltammogram, which is the raw signal. So that raw signal will have features in it. Now, in a bit, we're going to talk about features being proportional to the amount of material, but features are sort of parts of the raw signal which are strongly correlated with the material that you're actually trying to detect. So here I'm just putting in. Now, the reason I'm putting all these dots in is because I'm saying that there's actually many features that could be proportional to the amount of material. And you didn't have to use one or two. You can actually use quite a number of features. So what we're doing at Zimmer Peacock is we have a formulation that we think works. We do an excitation on it. We get the raw signal. Then we pass that raw signal to a database called Julie, which then allows us to really look at that, at those features and say, which feature gives us the strongest signal? Now, in the simplest way, it's just one feature, like peak height is proportional to signal and proportional to amount of material. But it really doesn't have to be that simple. In fact, your strongest signal can come from a combination of features. And when I say combination of features, you can look at the difference between two features, the ratio between two features, the product of two features, the sum of two features. There's lots of ways of combining features. But what we're doing is we're combining features to give us the strongest possible signal. So it's not just a sort of simple look at the raw signal. It's actually looking at different features within the raw signal, adding them up or making differences between them or ratios between them, so we end up with the strongest signal. So features, we want them to be equal to the concentration or the amount of material. Now what we're doing next is then we're checking signal versus concentration, because in the end we want strong signal versus amount of material. And so we will start off by measuring a low amount of material, a medium amount of material, and a strong amount of material, a high concentration. So low, medium, and high. Now, if your assay is really good and really developed, the number of, let's say, tests you need to make sure that your assay is actually working is actually 3. Just go low, medium, and high, and if you've got a signal that's versus concentration, then it's a good sign. Now, in reality, obviously in development, you actually want to do a minimum of 3 concentrations low, 3 concentrations medium, and 3 concentrations high. So in reality, you're often talking about doing not 3 experiments, but maybe 9 experiments. And if you want to do it sort of in replicates of 5, maybe 15 experiments. The more experiments you do, the more certainty you have, but you don't need an awful lot of experiments to understand that whether you have signal versus concentration. Now, the more replicates you do, you can then start including some error bars on it, so you can understand, I have a signal that's versus concentration, and this is my uncertainty because of my irreproducibility, probably of manufacturing, or my irreproducibility due to my experimental setup. And then you can also have a sense of how strong is my signal versus concentration, which we often call sensitivity. So there's often 3 parameters that we're at least trying to optimize on. Sensitivity, we want a strong signal versus concentration. We want to optimize on error. We want to have those error bars quite small. And we also, which I haven't talked about, want to have minimum interference from other molecules that might be in the matrix. Now, at ZP, I've just shown you a linear way where you have a formulation, you excite it, you do feature extraction, you do signal by combining different features together, and then you can do this check at the very end. Now, what you do is you actually then say, if it's good enough, stop where I am, and if it's not good enough, iterate around again. But actually, this is the whole point, that we call it Agile Biosensor development, that you actually iterate, assess, iterate, assess, iterate, assess. And you're actually doing that quite fast. Now, you don't iterate forever because the quality system alone will demand that you can't do this. But it does show you that it's not just a single look at an assay. We actually carry on improving the assay whilst working in on other parts of the total system. So I hope that's a good introduction to Agile Biosensor development from Zimmer and Peacock.